Hello. In this video, we're going to be looking at rates of change for quantities that are related to each other. So in this first example, we have the radius of a circle increasing at 3 centimeters per second. So we have a rate of change for a radius. We want to know the rate of change for the area of the circle at a particular moment. Now, we can easily relate these two quantities, area and radius of a circle, using the formula A equals pi r squared. But what we are looking for is a rate of change for the area in terms of time. So in other words, I'm looking for dA dt. I don't have a function for area as a function of time. I have a function for area as a function of radius. But I know, so this is what I'm looking for, and I'm looking for it at the specific moment when the radius is 4. I know that dr dt is equal to 3 centimeters per second. Now, I could, figuring out the rate of change of the radius of the circle, I can write a function for r as a function of time, substitute that in and get a function for area as a function of time and then derive that. But I don't have to. I don't have to do that because I can derive this formula for area as a function of radius implicitly with respect to time. So in other words, dA dt, if t is my independent variable, then I have to derive radius implicitly as well. So I get 2 pi r times dr dt. And I actually have values to substitute in here then. If I want dA dt at the moment when the radius is 4 centimeters, then that is going to be 2 times pi times 4 times that constant dr dt, which is 3. Now, you don't have to keep units in here like you would in a physics class, but just to note, the units will work out. If I have 4 centimeters and then my rate is in centimeters per second, then the overall unit is going to end up being centimeters squared per second, which is a change in area. So as an exact value, I could give this as 24 pi centimeters squared per second. Or if you wanted to give this to 3 significant digits, you could call it about 75.4 centimeters squared per second. This question doesn't specify, so it doesn't really matter. Obviously, if you don't have a calculator, just go ahead and leave it as 24 pi. But it is also reasonable here to give it as 3 significant digits. All right, let's look at another example here where it's a little more complicated maybe to come up with the equation. So we have the area of an equilateral triangle decreasing at a rate. So I'm going to say dA dt, the decrease in area, is negative 5 centimeters squared per second because it is a decrease. So I want the rate of change of the length of a side. Now, if the area is decreasing, the length of the side is also decreasing. So I should get a negative rate here. I want ds dt at the moment that the area is 250. This is what I'm looking for. So I need a formula that relates area of an equilateral triangle with the side length of an equilateral triangle. So let's think of what that looks like. So these side lengths are all the same. And I know that these are all 60-degree angles. So a couple of different ways you could do it. You could actually figure out what that height of that triangle is going to have to be as a function of s and go from there. But we do have a better formula for area here, and that's that the area is 1/2 the product of two sides times the sine of the angle between them. And sine of 60 degrees is a known value, that is root 3 over 2. So the area is root 3 over 4 s squared. So now I have a formula for area as a function of the side length. So I can derive this formula implicitly with respect to time. So dA dt equals 2 times root 3 over 4 is root 3 over 2 s times ds dt. So now I'm wanting to figure out what is ds dt when the area is 250. But here's where I have my first problem. I know dA dt, that's negative 5. I know s, I don't know a. So I actually need a second diagram here for this moment in time. So the diagram I've drawn here where I have s as variable, that just stands for any moment in this scenario, but I actually have one particular moment where the area is actually 250 centimeters squared. And I want to know in that moment, what is s? So s in that moment, well, I can use my same formula. 250 equals root 3 over 4 s squared. So in that moment, I have 1,000 over root 3 equals s squared. So the square root of that equals s. So for this one, I'm not going to bother dealing with exact values. So I'm going to go 1,000 divided by the square root of 3 is going to give me approximately 577, but I need to take the square root of that. So at this moment, the side length is approximately 24.0 centimeters. So this is the value that I'm going to substitute in to my derivative equation. So the change in area with respect to time is -5 centimeters squared per second, but once I divide that by centimeters, I'm going to get centimeters per second, which is what I want for my new unit, equals root 3 over 2 times that 24.0 times ds dt to figure out what that is at the moment that the area is 250. So just, I'm going to take that 24, I'm going to multiply it by root 3 over 2. Then I'm going to take -5 and divide it by this value. So I have approximately -0.240 centimeters per second is the change in the side length with respect to time at that moment. Notice that it is negative because it is decreasing. If you don't write the negative sign, that's fine, but then you have to write the word decreasing. There has to be an indication that you understand that this side is shrinking.